All right, so let's do a review for our quiz on pigeonhole principle. Okay, so remind you again, the formula, our main formula is when we want to calculate. So this is the formula, and let me tell you what each of these things represent. N is the number of pigeons. K is the number of holes, and M is what I will call the occupancy, how much there is going to be. It is an occupancy that what we should call an unavoidable occupancy. At least one of these has to have this many, of course. Yeah, that's what the problem is there is no good English word that says at least one has this many. There's no word for that, so I'm using occupancy as somehow the closest that I can get with this. Okay, so let's do some examples. So let's start with a deck of cards, and this is you need to know this. I mean, many of you probably know a deck of cards, but some of you might not so familiar with them, because a lot of questions are based in combinatorics and in these problems of calculating things. So a deck of cards consists of 52 cards, and they come in 4 different suits. So 4 suits. And that means that every suit has exactly 13 cards in there. The ace, the 2, the 3, up to the 10, and then the so-called 3 face cards, that is this jack, queen, and king. All right, so let's start with the first question here is if I draw 30 cards, so I'm drawing cards, and I want to make sure that I, for instance, have yeah, sorry, this is a bit weird. And how many will at least have the same? I forget what the B is from here. Okay, so draw 30 cards. How many will at least have the same value? So I'm turning 30 cards, and I'm looking how many 10s do I have? How many jacks? How many 3s? How many 4s do I have? Okay, and so the question is, am I guaranteed to have at least 2 of some, or perhaps I am guaranteed to have 3 of some? Okay, so let's think about what are the things here. So as always, we analyze this by determining what are our pigeons, what are our holes, and what is our occupancy. Okay, what are the pigeons? Well, that are the cards, okay? The cards that I'm drawing. What are the holes? So the value of a card, so I remind you, there is the 1, 2, up to 10, and then there's the jack, the queen, and the king, often denoted this way, okay? So there are actually 30 values. This is what I call the values of the cards. So these are the values. Okay, and so I have already calculated them, right? So let's see what we know already, and that's the 30 cards that I'm drawing. That's 30. The value is K is 13, and so the occupancy, that's the question, right? We don't know what it is. That's the question. How many do I have at least of the same value? Okay, in poker, to have 2 of the same kind, one says often, 2 of the same kind. So values of, if you know poker, you would call this a kind. 2 of the same kind, that's called a pair. 3 of the same kind, that's called a set. So how many? Let's see. Well, we apply the formula straightforwardly. We have to do this. Oh, sorry, K. So in this case, that is 30 divided by 13. Okay, so let me quickly tell you what the decimal value of that thing is. 30 divided by 13, that is 2.3. So 2.3, but we're taking the ceiling of this, so that's actually 3. So this means that if I take 30 cards, I will have at least 3 of a kind. Okay? Okay. that's the straightforward thing. Now let's continue with playing poker. So if you want, in poker, there's the notion of a flush, and a flush is five of the same suit. Okay, but I'm drawing these cards randomly, right? I cannot look at the cards and just take 5 hearts, say. That would solve it, right? No, the problem is to, in advance, say, okay, this many cards you can draw. Whatever you do, you can do this 100 times. I'm guarantee you always will have a flush. Okay, that's kind of the setup of the pigeonhole principle. Okay, so by the way, in real poker, you can only draw 5 cards. So in other words, it's very hard to get actually to draw a flush. That's why it's highly valued, a flush. If you have a flush, bet some money, okay? All right, but so, okay, let's analyze this again. What are our pigeons? What are our holes? And what's our occupancy? Okay? The pigeons. Well, there are the cards clearly, right? And then the holes. Well, now we're talking. We're trying to. The cards that we draw, we're gonna put them in piles. If you want, each pile a pile for each suit. So we're gonna put them according to suits. And then occupancy. Well, now it's a condition, and the condition is to have a flush. So let's see. Do we know the values here? Now be careful. Okay. So the flush. Okay. Let me start from the bottom somehow. The flush we know because it has to have 5. At least 5 is a flush. Okay, if you have 6, that's even a super flush, let's call it. Yeah. Do we know the number of suits? Yes, 4. Do we know the number of cards? Now be careful, you say 52 because there are 52 cards in the deck. No, I am not taking all cards in the decks. I'm drawing. So draw cards to get a flush. To get this flush, okay? So in other words, I don't know yet. That's the question that I'm looking for. So now, what I'm looking for is for the formula for n. Now, let's go to this original formula here. Let me write my formula here again, okay? So my original formula was this, right? The occupancy, the minimal occupancy of at least one of the holes is this, given by this formula. This calculates m for me. Now, if I want to calculate n, I explained this last time, there is actually, this formula is, these are the same, they're equivalent. The formula says the following is, well, what can go wrong if you take your k holes and you fill them up with m minus 1, less than actually needed, than you would want to. What happens then? Then you don't have enough, right? Just not. So if you put 1 to it, you have enough. Okay? So this formula can be used to calculate n. So in this case, now we know once we know the formula, it's 4 times 4 minus 1 plus 1. So that is 12 plus 1, that is 13. Okay? So, the m was 5, right? So it's, it's 16 plus 1, so it's 17. Sorry, I was looking at the wrong number. Okay? Well, that's how you find m. Okay, so let's do another one. Another typical setup is an urn filled with balls. And the thing is you cannot see the balls. And what often is you draw balls out of this urn or something like that. Okay, so suppose there are 4 different colors and 3 different sizes. So the balls can come in 4 different colors and in 3 different sizes. So the question now is, how many balls to draw to be guaranteed, so no matter how I draw them, and remember you cannot see what you're drawing, right? To have at least, to have 6 of the same, 6 the same. Let me just put it simply like that. Okay. Let's analyze this. The question might be not entirely clear yet, so let's see. It's sometimes you don't understand everything yet, but let's figure out what we know. The pigeons. Well, we are drawing balls here, right? At this huge big urn, we don't know, let's assume there are quite a lot of balls there. We don't have to worry about the number of balls. So we don't know yet. So, and the pigeons are the balls here, sorry. What are the holes? Well, we want them to be the same. What does that mean? So the same means same color and same size. That's when we call them the same, right? A red ball, a small red ball is different from a big red ball, right? They have to be same color and same size. So in other words, we can say the types. How many types are there? And then the occupancy, well, that's given now. We need at least 6 of them. Okay, this is numerical condition, so we just write down the number instead of, before it was a flush, we knew what that means, but this is just a number that I come up with. Okay, so do we know what the balls are? No. Do we know the types? What are the types here? The colors? The sizes? No, it's actually a combination of both. It's a color and a size. So types is if you want, a type is giving a color and a size. So how many are there? So let's think about it. How do you create this type? You choose a color, and then independently you choose a size. This reminds us very much of the product rule. So we have 4 times 3, that is 12. Okay? And so this, as we already said, f is 6, so we can use our previous formula here, this formula. So I'm talking about, this formula here that I'm going to use, right? So we see that n is equal to k, which is 12, times 6 minus 1, that is 5, plus 1, that is 61. So 61 balls, if I draw them, then I'm guaranteed. And so let's think about it. If I have only 60 balls, then what could happen is there are 12 different types, and I could have 5 balls of each type. And that would be 60 balls, right? And then I would not fulfill my condition. Okay, so I want to do one more question that I have not really done, but it's good to see one. So let's go back to these balls. I want to set this up again for my friend, and so I'm going to color the balls. And what I want to do is oh, sorry, I wrote it on the wrong side. I mean, color 30 balls. I'm going to take 30 of these balls and we're going to give them a color randomly. This is to make sure that it means you cannot just take a ball and make it happen, right? Something else, a machine is doing this for us, randomly choosing a color, okay? So that at least let's say 4 of the same color. So what's the question here? So how many colors can I use? Now, of course, I can use just one color and I'm guaranteed to have 4 the same, because that actually is 30 the same. On the other hand, if I take 30 colors, then it could very well be that every ball has its own color, and then I'm not the condition is not satisfied. So how many? Sorry, many fell out here. How many colors can I use? And I want to as much as possible. Let me not write that down. I'll say it. I say it just in words. But what's the best? As many colors as I want to make it as colorful as possible, but I still want to make sure that this is the condition is met. So okay, let's analyze this again. We have pigeons, we have holes, and we have the occupancy condition, right? All right, so let's see. What are the pigeons here? Well, okay, we're talking again about the balls. And we are just giving a color, so that's the holes. And what is the occupancy condition? Well, at least 4 of the same color. Okay, so that we know. So we don't know. Do we know the number of balls? Yes, actually, we've given 30 balls. So we know this one. What about colors? Do we know the colors? No, that's the question. Now, how many colors? So this time we have to find K. Now, so far the 2 formulas that we have here, I'll circle them again. This calculates m, and the other one calculates n. So what if you want to calculate k? Okay, I'm going to give you the formula, and I'll say a little bit about it, where it comes from. So the formula is the following. Well, here, we're going to, let's derive the formula, perhaps. It's good to see, so let's do it in purple here. So I'm going to use it from here. So I'm going to solve for k, in other words. So go to n minus 1 is k times n minus 1, right? I bring the plus 1 to the other side, and then I'm going to divide by n minus 1 both sides. And so that gives me k. K is equal to that number. So let me write it up here. So we have that k, I want the black. So k is equal to n minus 1 divided by m minus 1. Now, there's a problem, of course. In general, this number will not be a whole number, right? So let's just, for instance, think about this. Suppose I have, well, let's do it in this particular case here. Let's work it out here, what happens, okay? So remember, the formula came from in this formula solving for k. But it's not, the formula is not completely there yet. I'm going to make a slight adjustment, but it will be clear why. So let's do this in this case. So we would calculate this number, okay? So k would be 30 minus 1, that's 29, divided by 4 minus 1, that is 3, okay? 29 divided by 3, that is, I'll give you the value, 29 divided by 3 is 9.66. So if I use 9.66 colors, I'm guaranteed, for my 30 balls, I'm guaranteed to have 4 of the same color. How do you do a fractional number of colors, right? So I have to round this, but how am I going to round this? Now you might say, okay, I can always take the ceiling. But think about it. Is that the right thing to do? Remember, the more colors you take, the least easy it is to get your condition. For instance, if you take 30 colors, you're never going to get it's going to be very hard to get 4 of the same color, right? Randomly. So you want to, in other words, 9.66 is the maximum number of colors I can use. If you use more colors, it doesn't work anymore. Of course, really I can only take not 9.6 but 9. So the formula is that I have to take the floor of this number and not the ceiling. Okay, but the reason, the difference is here. See, when we talk about occupancy, we mean that one has to be at least m, okay, m or more. When we try to find the value of m or more. Here we want to do some, we want to restrict the number of holes. If we take too many holes, we don't get the desired occupancy. So we are gonna make our number of holes at most this much, and when we do at most, we have to take the floor, and we do at least we take the ceiling. That's the idea here. I just wanted to give you this formula that you see how it works. So in other words, we have to take this here, and the number is 9. Now let's double check, does this work? If I have 30 pigeons with 9 holes, what is then, let's work out what is this, 30 divided by 9, right? This is just straightforwardly working out the formula now. I'm using this formula, right? So this is m here. So 30 divided by 9. 30 divided by 9 is 3.3. And I'm taking the ceiling of that, so they get 4. I get exactly what I want, at least 4. Okay? I give you an example that because sometimes you have to find also the number of colors. Now, you don't have to use these exact formulas as this formula like I gave here. This formula, but I would write it down. It's good to have these 3 formulas. So I remind you, this formula, we have the formula so we have the formula that calculates m, the formula that calculates n, and the formula that calculates k. Okay. You can also try to reason by saying you have to have at least this and that. Especially with smaller numbers, it's easy to do it that way too. Okay, that's all for the preparation for the quiz. The quiz will be using these formulas basically in a real life situation, so to speak.